What's up, Trig? This is Mr. Carlson, C-Squared Mathematics, and welcome back. This is now the last week of trigonometry. Can you believe it? We made it so far in our trig studies that now it's the last week of trigonometry, and I'm sort of sad, just like a tad bit sad. And I think you should be too, because trig is amazing. And so I wish we can continue our study into trigonometry. There's so many more topics that we could go over, but we're going to end with these last three topics. You have 3 more lessons, 3 more videos of the course. And after that third video, there's no more video lessons, no more lessons at all. I know, sad day. So we're going to go through 7.5. Tomorrow is going to be 7.6. The next day, 7.7. And that's going to be the last couple of days. So 7.5 is what we call complex numbers in polar form. So we are going to now go back into the recesses of our mind and look at complex numbers. Remember Algebra 2? Remember Algebra 2.1 when we learned complex numbers and what complex numbers entailed, how to simplify them, how to graph them, the absolute value of them. We're going to review all of that today. And then we're going to get into more trigonometric complex numbers and how trigonometry really relates to complex number solutions. It's really an awesome lesson because what it does is it takes the bridge between algebra to trig. And it's so beautiful. I really, really love it. There's often times in algebra where we would simplify radicals and we couldn't simplify the radical anymore because it was imaginary. But now, no longer can we just bypass those. We are going to look at some radicals and actually simplify them in the complex numbers, simplify them in polar form. And we're going to go back and forth between them, convert between complex numbers to polar form to rectangular form, and so forth. Okay? Bell work, I only have one question there, then the objective essential question, the lesson, and then the summary. So this is the only question I have for bell work. So please write it down so we can get started. Awesome. So this question, the rectangular coordinates of a point are given. This is the rectangular coordinates. Find the polar coordinates and then express it in terms of theta with radian measures. So what do I do here? Well, notice how this is sort of, kind of, like a special right triangle here. And if you don't notice that, then that's a shame, but you should be able to notice that it's roughly a special right triangle. First thing I need to do is realize what kind of quadrant this is in. So this is the third quadrant, so I'm going to actually blow up this third quadrant. I'm going to draw my extending triangle with my little right angle. Okay, I don't really care what this theta is, to be honest. I'm just going to put it there. I don't really care what that reference angle is. That's not what I'm trying to find. I need to start putting in these. So my x variable is this. Negative radical 3, and this is negative 1. So since this is a special right triangle, you should already know that this will be 2. You don't necessarily need to know the Pythagorean theorem on that. But 2, that is my r. So 2 is my r. So since that's a special right angle, I can say r equals 2. And I'm going to use that information to start solving for my theta measure. Okay. Now the interesting thing is, just looking at this, you can really just look at your unit circle and see what angle measure this is. If cosine of theta equals negative radical 3 all over 2, and then sine of theta equals negative 1/2, all I have to do is just look at my unit circle. Okay, if I look at my unit circle, I already know that this is going to be 7 pi all over 6. Okay, I don't need to do my tangent, my inverse tangent at all or anything like that. I could, and I would still get this. But since this is a special angle, it's really all I have to do is just notice, hey, this is a special angle. These are my cosine and sine values. So I take those values, peer at the unit circle, and then I'm like, boom, 7 pi all over 6. So that's my theta. This is my r. My third step is to put them both together. My r is 2, and then this is 7 pi all over 6. Now, this is not what theta is, technically, and by theta I mean this. Remember, this is a reference angle, okay? What theta actually is this, okay? So this whole thing, that's 7 pi all over 6. If I want to know what the reference angle is, I just look at the denominator. Okay, well, that's 7 pi all over 6 is. So this reference angle is pi all over 6. All right, and I know that just by my unit circle and also just looking at my x and y values. I mean, I know that's got to be, since this is a special right angle, I know that's got to be pi all over 6. So that's my reference angle. So I didn't want to know that. I wanted to know my actual angle, not my reference angle. So don't get confused with this theta. This theta is not 7 pi all over 6. Okay? This whole thing, that's theta. This theta right here, we can call that like theta prime. That's pi over 6. So I see a lot of you kind of mixing that up on your quizzes. So maybe I didn't explain that adequately enough. I apologize, but just notice that that is like theta prime. That is a reference angle. My actual theta that I'm interested in is this whole thing. That's 7 pi all over 6. Okay? But that's my answer. Weird looking unicorn there. He doesn't look too happy. I'm sorry, but you know, are we all happy all the time? Maybe not. Okay, let's get started. So 7.5, I love this lesson. This is a great lesson. This is one of my favorite lessons to teach in trigonometry because it really does teach you the relation between algebra and trig. So how can I convert complex numbers in polar form? And then how does complex numbers in polar form relate to what we call mathematical chaos? Very interesting stuff that we're going to get into. Mathematical chaos is something that is just really almost just indeterminate. So when you look at quantum theory, a lot of it's indeterminate. So we can't determine based off of mathematical laws or physical laws the quantum realm. It basically, despite what Tony Stark does in Endgame, it basically defies a lot of our reality, and that's an issue. So it's what we call mathematical chaos. If you ever remember watching Jurassic Park, like the first version, not with Chris Pratt, like the very first movie, Jurassic Park, Jeff Goldblum is in the car with the one of the main characters, the wife of the main character, and he's explaining chaos theory with a glass of water. And so what he says is, if you dip your finger in a glass of water and put it on your hand, it may the water may run that way. But if you do it again, if all the same conditions are literally the same, so far as you know, but yet you dip it and you put it on your hand, but it runs a different way, there's so many conditions, even though it's unbeknownst to you, there's so many conditions that are just present on your hand, all the imperfections of your hand that make the water run. If you literally dip it, have that water droplet on your finger, you dip it right here, it could run this way, it could run that way, it could run this way, it doesn't matter. And we just don't know why that is, and that's why we call it chaos theory in mathematics. One of the most famous chaos theory sets in mathematics from complex numbers is what we call the Mandelbrot set. And so it's a very, very interesting thing. You could look it up on your own, the Mandelbrot set or something like that. And it's very pretty. I mean, if you just type in the Mandelbrot set, it's very gorgeous of what it looks like. And we're not going to be doing that here. We're just going to be doing the very foundations. But if you ever go into mechanical engineering and or quantum physics or some sort of physical field, you will have to do with complex numbers, and you will be experiencing what we call the Mandelbrot set. It's a very, very common set of complex numbers, but we can use it with in tandem of polar form, in polar coordinates. We can use it with complex numbers in polar form to try to determine where that droplet of water would go. It's very interesting stuff. We're not going to get into that here, but I just wanted to give you a preview of what the foundations a preview of the applications that we're going to be going through today. We're not going to be going through those applications. We're only going to be going through the foundations of those applications, unfortunately. So here's some other foundations to get started. Review complex numbers. So remember, complex numbers is a branch of mathematics using square roots of negative numbers. It was invented a couple hundred years ago, primarily by Euler. he was not the only inventor, but he was one of the big proponents of the imaginary number. He basically invented it so that he could start analyzing these complex numbers of what he called the complex numbers with square root of negative numbers. Okay, so what I wanted you to do is simplify the following. See if you can get all of these. Okay, I'm going to pause the screen here and then bring it up. See if you can get these. Because this is review. We did learn this in Algebra 2. So pause the screen, see if you can actually analyze these and simplify them, and see if you actually get the correct answer. Perfect. So you should get these answers. That's the square root of -1. So whenever I have a -1 underneath the square root, or really an even root for that matter, I have I. Okay, I squared is -1. I add these just like or subtract them just like I normally would with combining like terms, but I need to distribute the negative through. So I get this. I need a FOIL, but the middle terms go poofy. The reason why they do go poofy is because this is what we call a conjugate, a complex conjugate right here, where the numbers are the same, but the sign is different inside. So that ensures that I will get rid of all my imaginary numbers, so including the middle terms, and then I squared right here attached to that -4 is -1, just like this. And so that becomes a +4, 29. And then here it's just adding like normal, so that just means everything goes poofy, becomes 0. Okay, if you got all that correct, then you're awesome. You're right on your way to becoming an algebra star. All right, now plotting complex numbers. Remember, when we plot complex numbers, remember, this is review. When we plot complex numbers, I have a real axis, which is the same thing as saying my x-axis. And then my imaginary axis is technically my y-axis. So if I have something like this, what that means, guys, is that I just move it a and then up b units. Okay, I don't really care about the I. So this is the same point as saying 3, 4. This is the same point as -1, -2. This is the same point as saying -3, 0, because this is technically +0i. And then this is +0 in front. So this is the same thing as saying 0, -4. So given all that information, plot it. Let's see if you can plot it. Pause the screen, plot it, see if you can just do it really, really quick, and then we'll see what happens. Cool. So this is what you should get. Notice how I label them in their complex number form, not their ordered pair, because it's technically, you don't write an ordered pair in complex numbers. Their ordered pair is its complex number form. So we wouldn't technically write that. We would write the actual complex number form, which is what I did. And those are all the points. Okay? Very simple stuff. Again, just review. Let's move on to our last set of review here for complex numbers, and that is the absolute value of complex numbers. So this is the absolute value of complex numbers, and now it should be very familiar to you. I had a purpose for when I taught this to you in Algebra 2. What is that? That, my friends, is simply just your Pythagorean theorem. That is just your Pythagorean theorem. Why is it your Pythagorean theorem? Because if I have this right here, if I have a point, just a plus bi, if I want to know this distance from the origin, okay, that distance from the origin, what is that distance? That's just r. That's just your Pythagorean theorem. That's all it is, okay? And so this is very, very interesting because now we're going to actually combine this Pythagorean theorem with complex numbers now instead of just real numbers. And it's very fascinating, very, very fascinating. It's almost as if the Pythagorean theorem is the basis for all trigonometry. I wonder why that is, okay? Because it's a right angle. It's a right triangle, of course. All right, so interesting stuff. This is just simply distance, okay? It's a Pythagorean theorem, of course, but it's also the distance from the origin. So make sure you know that, from 0, 0. We are going to be, or in this case, 0 plus 0i. We are going to be utilizing this in the next couple of days, specifically tomorrow, actually, because this is right here. This is a segment, but honestly, it could be considered a ray. An array is the same thing as a vector, and that's what we're going to be doing tomorrow. Okay, so let's go through our example with this review question. Let's find the absolute value of these two examples, A and B. Okay, if I wanted to find the absolute value of A, these are where they are at, by the way. So what this is I'm just trying to find the absolute value of A, but I would have to make my triangle here. Okay, this is a triangle, right? So this distance is 3, this distance is 4, and I want to find that. Well, it shouldn't take a genius to know if I have a 3 and a 4 for my legs, what should my R be? Okay, my R should be simply 5 because it's a 3, 4, 5 triangle, but I'll show you. So this is the absolute value of Z, which is really the same thing as R, and this will equal 3 squared plus 4 squared. When I simplify this, guys, I know I'm going to get 9 plus 16, radical 25, which is just 5. Okay, 3, 4, 5 triangle. For B, same thing here, but just a little bit different. I'm going to have this extending triangle. So this is just -1 off to the side and then -2. So this is the same thing as the absolute value of Z, which is the same thing as R because it's distance. And so I'm really just taking -1 squared and then plus -2 squared. What this gives me is just radical 5. That's my R. Okay, very simple stuff. Pythagorean theorem, that's all it is. Okay, nothing too difficult for us, right? Awesome. So that's all review. Now let's get to my actual trig stuff. Let's go to town on my actual trig stuff. First things first, the polar form of a complex number, we will use what we call de Moivre's theorem. De Moivre's theorem. It's kind of hard. Sometimes some scholars say de Moivre. That's kind of weird. De Moivre. I say de Moivre's. De Moivre's. That's just all I say. I basically pronounce it as if the R is silent. So de Moivre's theorem. So this theorem is as follows. I can write the complex number right here. Let's put this in red. I can write this complex number in what we call a polar form. Now let's be very clear. This complex number is still rectangular form. So just because I have a complex number does not mean it's not rectangular. Remember, rectangular form is just x and y, but I can still have rectangular form with the complex number system. I don't need my real number system, my x and y system, my real number system to just have a rectangular form. I can have a rectangular form even with imaginary numbers, with my complex system. So this is complex form, or sorry, this is rectangular form. This polar form, this complex number is still rectangular form. This is what we call, obviously, polar form. Why? Is because it's using R and thetas, okay? Where rectangular form is using A and then B's, all right? So A and B's, rectangular form, R and thetas, polar form. So this is the formula that I'm using. It's honestly very brilliant. I was just shocked when I started learning this because the applications of it, you guys don't even know. But the applications of this is brilliant. I mean, it has so many geometric compilation applications of it. It just blows your freaking mind. And so we don't have the time to do it here. However, I will show you why and how we get this formula. So where A equals R times cosine and B equals R times sine. Why is that the case? Because B is going to represent your Y and then A represents your X. So, I mean, it makes sense that your A is correlated to your cosine because A is correlated to X, and your B is correlated to sine because B is correlated to Y. So how do I actually get this? Not just that, but from there to there. Because I know this is my Pythagorean theorem, what I just circled, right? That's my Pythagorean theorem, right? So that's my distance formula. So how can I get from here to there Well, if I use these definitions, specifically if I use cosine of theta in my complex form, cosine of theta equals a all over r. And if I use sine of theta equals b all over r. And if I could go even further, tangent of theta equals just b all over a. I can use specifically these two to simplify as follows. So I can multiply r to both sides, so a equals r times cosine of theta. And then b equals r times sine of theta. I can use this information to then go further. If this is z equals a plus bi, if this is z equals a plus bi, I can then put this rectangular form into what we call a polar form by using this information. So in r and thetas. So let's substitute. If this is a and that's b, I can say z equals my a, which is r cosine of theta, plus bi, this is going to be r sine of theta, times I. And then what's common in both terms, guys? R. So I can simplify this further by factoring out an r. So r times cosine of theta plus, let's move I to the front, I times sine of theta. And that is how we get De Moray's theorem. Isn't that amazing? This is kind of a preliminary De Moray's theorem. De Moray's theorem is more like, I'm going to show you in a little bit, mainly dealing with complex numbers and powers of complex numbers, essentially. It's basically just, he uses it over and over and over and over and over again. So feel free to look it up to know who he is. He's pretty intense. I like him. He's not on my wall, though. All right, so make sure we know this formula. Let's go to town and actually use this. Like, let's actually use this in a couple of examples, okay? So example 3, plot z equals -2 minus 2i. Well, we already did that, so that's amazing. Now what we want to do is write it in polar form. So this is in terms of I. So I'm just going to say this, terms of r, theta, and then I. So you will have these variables chilling in there, okay? So let's see what this is about. First of all, let's find my r, okay? Let's find my actual r equals. So if this is my thing, my triangle, my triangle, this is -2 and this is -2. Well, this is nice, and we should know this based on our special right angles. This is going to be 2 radical 2. Okay, since these are the exact same, 2 and 2, -2 and -2, whatever, it doesn't matter. If I wanted to find this, I know that this is going to be 2 radical 2. That side times radical 2. But just in case you did not know that, let's just use our formula. So this is a squared plus b squared. I already know based off special right triangles, it's going to be 2 radical 2, but I'm just showing you why this is the case. So my a is going to be -2. I square that. My b is -2. I square that. This is going to be 4 plus 4. This is radical 8. And I simplify radical 8 down. I want a prettier 8 here. I simplify 8 down to be 4 and 2, and this is 2 and 2. Since it's a square root, I circle 2. So this is r equals 2 radical, what's left over, 2. Just like I said. Ta-da! Okay, notice how knowing your special right triangles, very, very useful. Very, very useful indeed. Okay, that's my first step. My second step now is to find my theta. I don't even know what my theta is. How can I find it? Well, let's use my tangent, my inverse tangent. So I will use my inverse tangent of, I'm going to switch the definitions here though, b all over a now. Same thing as y all over x, but now I'm just using b all over a. This will equal my theta. So my theta equals all of this. So I will have inverse tangent of -2 all over -2, which is the same thing as saying the inverse tangent of just 1. Now, if you already don't know this, you should, but this is just going to be pi all over 4. If you did that on the calculator, you would get pi all over 4. But wait, this is a problem because pi all over 4 is right here, okay? It's in the first quadrant. So this right here is quadrant 1. I don't want quadrant 1 though, do I? No, I want quadrant 3. So how do I get pi all over 4? How do I get pi all over 4 to make it into this angle? Well, I could do a couple things. First of all, I can use just my unit circle. Where else does tangent equal 1? What other angle of tangent does it equal 1 on the unit circle? Positive 1. You could use your trig table of common angles. You could use your unit circle if you want to and just evaluate it that way. Or you can just simply say, well, I'm going to take pi all over 4 and then add pi. This will equal 5 pi all over 4. 5 pi all over 4 is not in quadrant 1, but this is in quadrant 3. And that's what I want. Okay? So this is my angle. This is my R. My third and final step. My third and final step at the bottom is essentially trying to put it back in polar form. So that's what I want. So I'm given this. I want to put it in polar form. So this is Z equals, remember my formula is this. I'm just going to put it off to the side. My formula is R times cosine of theta plus, and then I times sine of theta. That's my R, that's my Z. That's my polar form of my complex number. So I take that. What's my R? This is 2 radical 2. What's my theta? This is going to be in parentheses cosine of theta, which my theta is 5 pi all over 4. And then plus I sine, and then 5 pi all over 4. That is my polar form, written in theta, written with R's, and written with I's. Okay, I'm done. That's all I need to do. Yay! All right. Not too terrible, yeah? Awesome. So let's move on. Let's erase this. Now let's actually get to what if I want to write it, yes, in polar form, but I want to go a little bit further and I want to evaluate. Okay, so when it gives you now a polar equation, so it gives you a polar, and now you want to go to rectangular, what you have to do is what we call evaluate it. Now, in the last slide, I didn't evaluate anything, actually. I just kept it in polar form. If I wanted to put it back in rectangular form, what I would do is evaluate it. What do I mean by evaluate it? Well, let's find out. So this is Z equals 2. What is cosine of 60 degrees? You should know this. You should not need your unit circle to do this. Okay? You should be thinking that this is 1/2. Guys, by the way, if you're still struggling with understanding these values almost at the top of your head, just think one thing. All you need to know is that sine of pi all over 6, or sine of 30 degrees, is 1/2. Literally, that's the only thing you need to know in order to get all other trig functions. All other trig functions. Because you already know that the pi over 4s is just going to be radical 2 all over 2 and radical 2 all over 2. Sine and cosine are the exact same thing for that. If you want to know though the pi over 6s and the pi over 3s, all you need to know is that, because that means cosine of pi over 6 is literally just the opposite. If this is just radical 3 all over 2. And then if I do cosine of pi over 3, cosine of pi over 3, it's again just the opposite. It flips it. So it's not going to be radical 3 all over 2. It's going to be 1/2. And this I times what's sine of 60 degrees, it's not going to be 1/2. It's going to be the opposite thing, which is radical 3 all over 2. That probably doesn't help you at all. Maybe it does. To me, it does. I remember my college professor one time telling me that, and I was like, wow, that's actually very brilliant. I never thought about it that way. And I've never struggled with the unit circle since, to be honest. There's also what we call a hand drive, a 5-hand drive, where basically you go through in the quadrant, it's like this, and then you kind of find out like this is your like 0, this is your pi over 2, this is your pi over 6, your middle finger is pi over 4, and then this is your index finger is pi over 3. I never taught you that, but maybe if you're interested, I could teach you that, but it's not really useful. So right here, I just distribute it through. All I do is distribute it through. So right here, this is just going to be 1, and then plus, and then the 2 goes poofy, so this is just I, and then radical 3. Guys, seriously, I'm done. That's it. This is what z equals. So this right here is in what we call rectangular form. And it can still be complex. Okay, it's rectangular form. Obviously, it's complex. Remember my complex symbol is this. So that's my complex symbol, my complex number system symbol. It's still complex, but it's still also rectangular form, okay? 2D, whereas polar is kind of like 3D almost. It's kind of like a sphere or a sphere, whatever. All right. Let's erase that. That's how I evaluate it. That's how I go from polar to rectangular. I just evaluate my trig functions. Very simple stuff indeed. Now let's go into products. Let's go through a little bit more advanced stuff. Are we ready? So advanced stuff says this. This is my formula for products. And this is also on your formula sheet, for your actual master formula sheet on Google Classroom, by the way. So make sure you know that because that's on that sheet. Very interesting. So Z1 will equal R1 times cosine 1 plus I times sine theta 1. This is like my first thetas, like my first one. Everything is 1. My second, if I'm given a second polar form, whatever, a second just plot of my polar graph. These two complex numbers are in polar form. If I give in another complex number in polar form, I can multiply z sub 1 times z sub 2 using this formula. Okay? You don't necessarily need to know the moduli and the arguments. I kind of skip past that. You don't necessarily need to know that. The moduli is just really the r's, and then the arguments are like this. Don't need to know that too much. That's like really advanced math. You analyze the moduli and the argument. You don't need to know that. All I need to know is how to use a formula, and that's all you need to know too. So I'm given these two things. I'm going to write out my formula here. So z sub 1 times z sub 2. This will equal r sub 1 times r sub 2. And then in brackets, cosine. And then this is theta 1 plus theta 2. And then this is plus I, and then sine, and then theta 1 plus theta 2. So this is my formula here, and we're going to be utilizing that formula as such. The hardest part of this, guys, is just recognizing what thetas are which thetas. Well, this right here, this is your R1, this is your theta 1, and this is your theta 1. Okay? This is R2. This is your theta 2, and this is your theta 2. It's just like that, just as simple. Okay? So if I want to find z sub 1 times z sub 2, because that's the product, that's what I'm doing, finding the multiplication or the product, I take 4 times 7. In brackets, I write cosine, and then 50 degrees plus 100 degrees, and then plus I, and then sine, and then same exact thing, 50 degrees plus 100 degrees. Theta sub 1 theta sub 1 plus theta sub 2. So it is literally that simple, nothing too fancy for that at all. And then I'm just going to be simplifying it out. So 4 times 7, of course, is just 28. And then cosine, and then this will become just 150. 150 degrees plus I, and then sine of 150 degrees. And that's it. If I wanted to then put this and evaluate it to find the resultant, something that we're going to be doing tomorrow, the resultant, what we call vector. the resultant vector, I could just simplify this, and then I could get my rectangular form of when I multiply these, I find my rectangular form. That's kind of advanced. I'm not going to do that, so I'm just going to leave it as this. Actually, I'm going to box this. Sorry. It's my actual answer. I guess I'm just going to have to finish the cloud now. Okay, but that's my answer. Smiley face. Okay? Sorry about that. But that's it. That's all there is to it. It doesn't say to evaluate it, we want to leave my answer in polar form. So that's polar form, so I'm done. So let's erase. Now let's get into what we call quotients. So this is products. Let's get into what we call quotients of complex numbers. If products, I'm going to add them, add the thetas together, but multiply the r's. That means with quotients, I'm going to divide the r's, but subtract the thetas. Okay, so this is exactly what I have. I divide the moduli, my r's, and then I subtract the arguments, which is my thetas. And that's all you need to know. Okay, so let's now transition into my actual example. Make sure you get this down. Write it down. Pause the video if you need to. All right. This is my example. I'm not going to write down the formula though, because I feel like we should be able to. If you wrote down the formula, then you should be fine. So I'm going to divide my r's. So I'm going to take 12 all over 4. You always take the z sub 1 divided by the z sub 2, and you always take the theta sub 1. These are the theta sub 1, and then you take the theta sub 1, subtract the theta sub 2. Okay? So that means in parentheses, or brackets rather, I have cosine, and then I have 3 pi all over 4 minus pi all over 4. This is going to be plus I, and then sine, and then exact same thing. So 3 pi all over 4, and then minus pi all over 4. So really all of this is going to be 3. And then I'm going to actually start combining these. So cosine, what is that? Well, if we need common denominators, right? Or they already have common denominators, so that's great. So actually, we don't need to do anything more than that. That's fantastic. Sometimes they don't have common denominators, and you would have to combine them with the common denominators. But this is great. So 3 minus 1 is just 2. So this is just pi all over 2. Okay. And this is plus I times sine, and then pi all over 2. So this is polar form, and they do want you to leave it in polar form. Now, just in case, maybe what if they do want it in rectangular form? This is in polar form. Let's just say they do want it in rectangular form, yeah? So if they do want it in rectangular form, then that means you will evaluate this, okay? So what this is in rectangular form would be equals, this is 3, cosine of 0 degrees, it's going to be your quadrantal angle there. So what's the x coordinate of your quadrantal angle of 90 degrees or pi over 2? That's just 0. And then what's your y coordinate of that? Well, that's just 1. So I and then times 1. Okay, so this actually equals just 3i. Okay, this is your rectangular form. All right, this is also what we call the resultant, but again, we're not going to be doing too much with this, at least today. We're going to be kind of tampering around with it tomorrow when we go through what we call vectors, a highly intense physics thing. Okay, awesome. Notice it did not ask for a rectangular form. I just did that just because I wanted to. Your actual answer is your polar form right there. That's your actual answer. I want to make that very clear. All of this, that's your actual answer. Awesome. So let's go through our last couple examples here. We will go through a little bit more complex stuff called powers. Powers of a complex number. Are you ready? Powers of a complex number. What is it? Load. Okay. So this is the powers of a complex number. It is the pinnacle of De Mornay's theorem. Now, previously, we did kind of go through like maybe a subset of De Mornay's theorem. Like De Mornay uses De Morve uses, obviously, this polar form of complex number. So this right here, my cursor is, that is your polar form of complex numbers. Obviously, that's what we've been doing over and over and over again with quotients, products, and just switching back and forth between rectangular and polar. But he uses that to expand upon it in the power form. So what if I want to do powers? It equals this. Now you may be thinking like, what the junk? What is this even used for? Again, it's used for complex indeterminate chaos theory, okay, with a lot of physics involved. The Mandelbrot set is probably the most important one that is using complex numbers in polar forms. Very interesting stuff. So I'm going to give you an example here, and I'm going to show you what this is. I want to write this in rectangular form. How do I write this in rectangular form? Well, both of these equations, as you can kind of see, both of these forms kind of bounce back and forth. So you could use this one, and this is the one that they actually give you. So notice how this is this, right? So I'm going to take this, and I'm actually going to equal that. All right, I'm going to equal that. And so when I do that, and then when I simplify it, then I'm going to simplify it and evaluate it to my rectangular form. So I'm going to go from here, which is what they give me. They give me this form where in brackets, your exponent is up top. And then we're going to equal it to this form, and then we're going to move that form and evaluate it to my rectangular form. Sounds good? So this, boom, 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 boom. So I'm given this. Let's go to town on trying to find out what this equals. So my r to my n power. Well, my n power is just 6. Your n is like your exponent here. Okay, so I have 2 to the 6th power. All right, 2 to the 6th power. In brackets, this equals cosine. And then right here, I have n times theta. So my n is 6, so that means it's 6 times my theta, which is 20 degrees. And I'm going to do the exact same thing with my sine function. So plus, and then I, and then sine of 6 times 20 degrees. Let's simplify it out. What is 2 to the 6th power? That's just 64. You can just plug in Desmos, plug in your calculator. No big deal. And then I have cosine of 120 degrees. And then plus, same thing for sine times I of 120 degrees. So now that I have this, I'm now going to transition this into my rectangular form by evaluating. So when you evaluate, okay, when you evaluate this polar form of complex numbers, that is when you're transferring it to my rectangular form. This is my polar form, all right, of my complex power. Now what I want to do is transition that to my rectangular form. So this equals 64. Now what is cosine of 120? You can just use your trig table of common angles, or you can just use your unit circle. Cosine of 120 is -1/2 because it's in the second quadrant and cosine's negative there, plus I, and then sine of 120, it's going to be positive, but that's just going to be radical 3 all over 2. Okay? All I have to do is just simplify through. So distribute that. That's going to be -32, and then plus, this is just going to be 32, and then I, and then radical 3. This is my rectangular form. Okay? So polar form, where my cursor is, that's polar form, polar form, polar form, polar form. It's in R and then also thetas. This is an A and B form, so that's my A, my real part, and that's my complex part, my 32 radical 3 times I. Okay? That's my complex part, rectangular form. Not too bad, right? Not too bad. Now, you may ask, why is this starred? You ask. It's because this is going to be on your test. So I'm starring this because I know for a fact this one is on your test. You're going to have to know how to transition between finding the power of a complex number, given your polar form, and then transfer it to a rectangular form. We'll do one more example, and this one is also, or something similar, is also going to be on your test. This is our last example for today. This one right here, what is it? So I want to find, using De Morvay's theorem, what 1 plus I quantity to the 8th power is. Now, you may be asking, well, if they want it to be in rectangular form, can't I just not use De Morvay's theorem and then just multiply all that out to the 8th power, like 1 plus I times 1 plus I times 1 plus I times 1 plus I times 1 plus I, and so forth? Can I just do that and multiply it all out? Yeah, absolutely. Go for it. Call me back after lunch because it's going to take you at least 30 minutes, okay? So it's going to take you a long time because, and why would we want to do that? You're going to have to FOIL all that out if you did it that way. If you literally did to the 8th power, you just multiplied 1 plus I times 1 plus I times 1 plus I times 1 plus I. If you FOILed all that junk out, you would, yes, get a rectangular form. But why would you want to do that? Because it takes so much time. An easier way to do that is using De Morvay's theorem. And this is a beauty. When I first learned this, I was like, what? I was like shocked. I was so thrilled that what I'm doing, it was like amazing to me. So let's take this in step by step. I want to essentially write what I'm underlining, or rather what I'm boxing here, not to the 8th power. I want to write this and I want to put this in polar form. Because when I put this in polar form, that means when this is in polar form, it's still to the 8th power. And then I can use De Morvay's theorem to go from what I did from the last slide, use De Morvay's theorem, the complex number in polar form, to the 8th power. I can then implant that 8th power inside my formula, just like what I did in my last slide. And then I can simplify that and evaluate it to get my rectangular form. Okay, do you understand what we're doing here? So we're taking just this box, 1 plus I. I'm going to put that in polar form. I'm now going to then use that polar form and implant it in my De Morvay's theorem using to the 8th power in the complex number polar form. I'm going to simplify that complex number polar form to the 8th power using De Morvay's theorem. So I'm going to take that 8th power and implant it into my formula so it's no longer to the 8th power. That's what we did literally in the last slide. And I'm then going to evaluate that simplification to become a rectangular polar form. I literally just did it. The only thing that's different from this slide to the last slide is that I'm going to transition this to polar form and then go to De Morvay's theorem. I was already given a polar form in the last slide to the 6th power, and then I transitioned it to rectangular form. I'm not doing that here. I'm doing one additional step. So are we solid? Can I kind of break it down for you there? So the first step is, first, I need to put this in polar form. In order to put it in polar form, I need to find my R. I need to find my theta. So my first step is to find my R. So that's what I'm going to do. Find my R. How do I do that? I use R equals my radical and then a squared plus b squared. Of course, how to find my R? I use the Pythagorean theorem, silly. So what is my A? My A is 1, so 1 squared is 1. My B is still 1, so 1 squared is 1. So that means my R is simply radical 2. Okay, perfect. This is my R, not my answer, of course. It's not my actual rectangular form of complex numbers. It's just radical 2. Now my second step is to find my theta. I want to find my theta now. How do I find my theta? Using tangent, inverse tangent. So the theta equals inverse tangent of b all over a, which in this case is just 1 all over 1, which is just 1. And this does equal pi all over 4. Now we have to wonder, is this the same quadrant that we want? Yes, because 1 for my A and then 1 for my B is in quadrant 1. So it does look something like this. This right here is 1 plus I. Okay, and so what I'm doing is I'm making my triangle. I know my R is radical 2. This is 1, this is 1. That my theta I just found, my theta right there is pi all over 4. You see what we're doing here? Just kind of abstractly. So now I got my pi over 4, my theta. I found my r, so that's good stuff. Now I'm going to do my third step and transfer it to polar form. So this is my polar form step. So how do I transfer it to polar form? I take 1 plus I just in polar form. Notice it's not to the 8th power yet. We will do that eventually. And this, of course, is going to be r times my cosine of theta plus my I times sine of theta. So this is my polar form, kind of de Mornay's theorem part 1. All right, so I'm still doing de Mornay's theorem part 1. This equals radical 2, and then cosine. My theta was pi all over 4, okay, plus I, and then times sine, and then pi all over 4. So this was my de Mornay's theorem part 1. We already knew how to do that in the first couple slides. Now let's in polar form, let's do the fourth step. And this is what we started to do in the last slide. So everything right now, steps 1 through 3, we already did that in the previous first couple slides of this lesson. Step 4 is where we're going to now start the math where we learned in the last slide. So now I'm going to look at the whole thing, 1 plus I to the 8th power. Okay, now I'm going to do it to the 8th power. So that means I'm going to take radical 2, all of this, and then cosine of pi all over 4 plus, and then I, and then sine of pi all over 4. It's really slow, and it's kind of driving me insane. All to the 8th power. So that's what it will look like. So I'm taking just what I found, the polar form, to the 8th power. So let's start simplifying this out. Using de Mornay's theorem, okay, using de Mornay's theorem, I'm going to put this like in purple here. Using de Mornay's theorem, what I have, just like what I did in the last slide, I have radical 2 to the 8th power. Okay, radical 2 to the 8th power. This is going to be cosine, and then I take 8 times pi all over 4. This is the same formula that we learned in the last slide, the power formula, plus I, and then sine, and then this is 8 times pi all over 4 as well. Okay? So now notice my 8 kind of gets implanted into my formula. And that's what I wanted to do, just like what I did in the last slide. Now you could do radical 2 to the 8th power. You can simplify that however you want. Technically, this is just, technically you can rewrite this as 2, and then this is 2 to the, I'm trying to think about the index. I think this is probably just going to be 1/2 or 1/8. So 2 to the 1/8, I believe. Is it 2 to the 1/8? I'm pretty sure. You can simplify that to be 2 to the 1/8. And then it's definitely not 2 to the 1/8. So I don't know what I'm talking about. Maybe I'm just maybe my algebra is just getting too flustered because I just finished my algebra lesson. So basically just do this on the calculator. That's all I can say. I know there's a way to rewrite that to make it there you go. Okay, now I'm thinking about it. Okay, so it's 2. I was like, I cannot move on without actually knowing this. Radical 2 is the same thing as 2 to the 1/2, and then this is to the 8th power. I multiply those to be 2 because that's power to a power, and that would just be 2 to the 4th, which just equals 16. There you go. Okay, I was like, what is going on here? So that's how you do it. So that would be 16. Or you could, like I said, just put radical 2 to the 8th power, and it would still equal 16. This right here, you need to simplify that. That would become 2 pi. So this would be cosine of 2 pi. And then this is going to be plus I, and then sine, and then 2 pi. Same exact thing. And then we just simplify it as such accordingly. So 16 cosine of 2 pi is just 1 plus sine of 2 pi is just 0I. And so what this equals is simply 16. Okay? It just equals 16. So that is technically my rectangular form. If I wanted to be a little bit more specific, I would say that this is 16 plus 0I. That would be a little bit more specific, I guess. But it doesn't matter. It's my my rectangular form. So there's no imaginary numbers there. So what does that mean? It means if you literally multiplied 1 plus I times 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 1 plus I all the way to the eighth, like 8 times, you'd get 16. See how much simpler it is? Just use your math, like use your De Mornay's theorem and everything. So I hope that makes sense. That's amazing. I love that kind of math. So let's erase, pause the video if you need to get it all down, but let's erase and let's get into our summary. So what did we learn today? We learned a lot of things, like a lot. We learned how to plot complex numbers in the complex plane. Well, we reviewed it. Find absolute values of the complex number. We learned how to write complex numbers in polar form, De Mornay's theorem part 1. Convert a complex number from polar form to rectangular form. We learned how to find products of complex numbers, find quotients of complex numbers, and also find powers of complex numbers. All right, remember, retakes are due this week, and it's available until next Monday from the polar quiz. If you have any questions on that, let me know. Be sure to review your notes today because the homework quiz, though it's optional, will be tomorrow. And I think you guys should probably try it. It's not too difficult of math. It's pretty simple, straightforward, plug and chug. Guys, this is Mr. Carlson. Be sure to like and subscribe. Make good choices.